All right, so again, this is Ken Kodelik with Primus Wind Power, and this is the Primus Wind Power hybrid and off-grid webinar for wind power. My information is here on the screen, my email contact, my direct telephone number, and also the tech support number is right here also. So if you have specific technical support questions, you can get a hold of our tech support department right here from this direct line. So we did purchase the air turbine from a company called Southwest Wind Power, which was around for many years in January of 2013, and we've been building these turbines, improving them as well as making changes and doing a number of things over about the last 2 years since we purchased the company. We are a division of Primus Metals, which is a American-based company out of Denver, Colorado, which was established in 1989, and our factory is in the same location as the Primus Metals precision metal manufacturing factory. They service the aerospace industry and defense industry and so on with precision metal products. So it was a pretty easy transition to start building these wind turbines. Company mission is just to provide a reliable, robust product that has great value, as we have to compete with solar, which is so low in price now, as we all know, and we're constantly innovating, making the product better. A few updates from the industry. We did add the Air X Marine line back into the portfolio at the beginning of this year. I'll explain why we did that here in the upcoming webinar. We are working on monopole tower designs for the Air unit. In process, we are testing this concept that you'll learn about called the hybrid solution at the National Renewable Energy Lab, NREL, which is in Colorado. We do have a turbine flying there on a monopole tower, testing that concept with solar and wind combined, and looking at that data. And just so you know, the oil and gas industry in the United States and Canada is expanding rapidly, and including solar and wind, especially wind, into their SCADA platforms, their off-grid platforms. That's a big expanding market for the industry. The Whisper line, which was made by Southwest Wind Power, was sold. Some of you may remember that turbine was sold to a company in India called Luminous Renewable Energy. If you need contact information for that, I'm happy to provide. They have a contact here in the U.S. who's not only distributing their product but also fixing Luminous turbines. And I know a lot of folks still think that we own that line, but we do not. But I can provide information for you. The Skystream line as well, which was made by Southwest Wind Power, is now purchased by a company out of Oregon called Exeris Wind. And if you need contact information for them, I can help you with that as well. And as far as we know, Southwest Wind Power has discontinued all operations as of March of last year. They are no longer in business. So there's the quick update from the industry. So now let's talk about the wind turbine itself. It is a 3-bladed wind turbine. It's what we call a micro turbine. It's an upwind turbine, meaning the wind comes in from the upwind direction, which would be this way, across the face of the turbine and the blade set across the nose cone, and then down through the nacelle, that's the body of the turbine here, hits the tail, which then turns the wind turbine in the direction of the wind, keeps it, as we say, on the wind. So nose cone right here is important because it helps to improve the aerodynamics across the face and the blade set. It also helps to keep any water infiltration through the bearing set and the shaft. So it's important to have a nose cone on the face. It just clips on. They're really inexpensive. So if it does come off or it doesn't get put on right or something, it's important to have that nose cone on there. 3 blades, 1.2 meter rotor diameter turbine. We have 2 different blade sets for the two different turbines we have. I'll talk more about that later in the webinar. Then you have your bearing set. This is your face. And then your stator right here, your shaft with the neodymium rare earth magnets around the shaft. This is your circuit card and your rectifier. The turbine actually produces what we call wild AC, which is unregulated AC, 3-phase AC. It goes through the rectification process here which then produces 12, 24, or 48 volt DC through the rectifier. This circuit card up here also controls what the turbine is doing in terms of the battery voltage. The turbine is always looking at battery voltage to see if it should turn off or turn on, or it's also looking at RPMs to go into overspeed protection. We'll talk a little bit more about that in a little bit. It does have an O-ring, so the nacelle is sealed through the face. Right down here is your yaw bearings, and then here is the yaw assembly where the 3 wires then come out of the turbine down to the battery bank. So that's the basic components of the turbine. There is the air turbines and the marine turbines. There are internal differences, but the external differences will be the blade set and the color. All of our marine turbines are coated with a special airplane paint, 2-part double coating process for corrosion resistance, and they are white. All the land turbines are just the gray cast aluminum housing, the basic finish. So when you look at the turbines, you'll notice that's the difference. Here's what we call our arrival kit. It comes with everything you need to set up the turbine on the tower, including the hardware, which is basically just Allen keys. So this is the Air 40 turbine with the little wider blade set. It's designed for low to moderate wind speeds. This is the land turbine you can see in the gray cast aluminum color. There's your yaw assembly. Like I said, 3 wires, one of them being ground, then your positive and your negative, down to the battery bank. This is a vibration dampening pad. It goes inside the yaw assembly here. It comes in the yaw itself, and then you have your nose cone, which is gray for the land, white for the marine, and your hub. There are 2 different hubs, one for the Air 40 and the Air Breeze turbine, and another different hub for the Air 30 and the Air X turbine. The way you tell the difference between the hubs for the different turbines is the Air 30 and the Air X turbines have 2 holes in the hub as well as in the root of their blade, and the Air 40 and the Air Breeze turbine have 1 hole in the root and 1 hole in the hub. So the very easy way to tell the difference. That's a common question that we get from our customers because there are so many of these turbines out there, over 150,000 of them in the field. Customers will call up and wonder, okay, which blade set, which hub do I need to purchase if I need to buy a new blade set, and so on. So keep that in mind. Here is the assembly. This is the Air 40 assembly. You see 1 hole there and 1 hub nut and hub screw, so it goes in here. You assemble the blade through the blade root onto the hub, 1 bolt through there, then it gets assembled onto the shaft, then the jam nut goes over the shaft, and then you snap on the nose cone over the hub. Very simple assembly, most likely less than 5 minutes, and then that whole assembly goes onto the tower itself, the 1.5 Schedule 40 or Schedule 80 pipe of the tower, and then the yaw gets clamped down onto the tower, and you connect the wires. So relatively easy assembly and disassembly for that matter for folks who are doing this in the field. Just a real quick reminder that the air turbine has its own internal charging system that turns on and off the turbine, so you actually directly connect the turbine to the battery bank. There are some recommendations I will talk to you about as to what you put in between, but it does not go through the PV charge controller. It goes directly into the battery bank. The PV then connects into the battery bank itself through a charge controller. Then you have the inverter here. If you have AC loads, if it's DC, it goes directly into the house or the small cabin or the sailboat. And again, if it's AC, then you have an inverter. So it's a very, very simple connection process for the turbine. Very, very simple wiring and easy installation. Standard system line diagram here. As you can see, I recommend a breaker or a fuse and a stop switch between the turbine and the battery bank, sometimes even an amp meter. We'll talk more about that. Battery disconnect as well is sometimes a good idea. All of these things are recommended, and if a dealer is going to install this, typically they'll put in a simple battery disconnect, fuse breaker, and a stop switch, and even maybe an amp meter, but it's not necessarily you have to do that. You can actually connect the battery bank directly, the turbine directly to the battery bank. A breaker is important in between. Anytime you're connecting an electrical device to a battery bank, you typically want to have a breaker, but it can be as simple as connecting it to the battery bank. As you can see here, this is a hybrid solution line diagram, so you can see that there's the PV array connecting to the battery bank through the PV charge controller, and then that turbine array is connected as well through into the battery bank, but on a separate system. So very simple line diagram. This is all in the manual, so you can review this as well. So one of the things I was talking about is a stop switch. We offer a single pole, 3-position, DC rated stop switch. We call it a break before make stop switch because it is actually a direct short to the windings. The turbine is an electromagnetically braked turbine. There's no mechanical brake on the turbine. It's braked by the magnetic of the stator itself. So when you brake the turbine through the circuit card, that's basically an electronic brake. But you can also brake the turbine through what we call this stop switch, which is actually a direct short to the windings. And here's how it works. You just right here you have that pole, that single pole, and you go from the run to the stop switch through open circuit, and then that sends in a direct short to the windings, meaning that you're actually disconnecting the turbine from the battery bank. So that's a direct short. And it's important to have a stop switch in line, especially for marine turbines, because there's going to be conditions on a sailboat where there's a big storm coming in, or it's at night and perhaps it's really blowing, and because the turbine is connected through the tower down to the hull of the boat, you could have some vibration into the hull of the boat, which may bother somebody who's sleeping on the boat, so they have a stop switch so they can take care of that. But also in a land condition, if you're going to be away from your cabin for a long period of time, or if there's a really big winter storm coming in, there's a few conditions where you might want to hit that stop switch on your turbine, as well as doing maintenance and that sort of thing. It's a good idea to have this simple stop switch in line. It's a very relatively inexpensive part. It's like $30, $25 for this part. So I recommend putting a stop switch in line. I also recommend putting a analog amp meter and a circuit breaker in line in your turbine. Again, very inexpensive parts. These are $20, $30 a piece for these parts. Relatively simple to wire. An analog amp meter is good. It's a fuel gauge type amp meter. The reason why I recommend an analog amp meter is because there's no parasitic draw from the amp meter off the battery bank, as opposed to like a PEM, a power energy meter, a PEM, P-E-M. There is a minimal parasitic draw off the battery bank, so if you have a small system, or if you're a small battery bank rather, or if you're away from your system for a long period of time, and you have that parasitic draw, not a good idea. So that's why these analog amp meters are good, especially for small systems. And then this is just a simple breaker with a pop-out reset switch, which is right here. A very simple part, yet it's important to have in line with your system. So we were talking before about the potentiometer and the system regulation and how that turbine turns on and off. I'm going to go back a couple slides and show you where this potentiometer is located. If you look at the turbine here, it's lying on its side. The potentiometer screw is this part right here on the side of the nacelle, the body of the turbine. One other thing I want to point out on this slide is on the bottom of the turbine right here, I know it's kind of hard to see, but there is an LED light. For an Air 40 and Air Breeze turbine, it's a green LED. For a Air 30 and Air X Marine turbine, it's a red LED. Okay, and I want to point out these two things. The potentiometer screw here, which you can adjust the potentiometer voltage regulation set point. I'll explain that. And this LED light. I want to talk to you just for a sec about that LED light while we're on this slide. That LED light is your light that tells you what the turbine is doing. It's a good troubleshooting light. So when you call into tech support or you call in and say, hey, I'm having problems with my turbine, if this occurs, you can, one of the first questions that somebody's going to ask you is, well, what's the LED activity? And so that means if the LED on the turbine is solid, not blinking, it's lit up and it's solid, that means your turbine is working, it's up to speed, the blades are spinning at a high enough RPM to where you're exporting energy down to your battery bank. So that means that it's solid and it's working and it's sending energy to your battery bank. It could be a tenth of an amp, it could be half an amp, it could be 9 amps. It just lit up and it's sending energy to the battery bank. If that LED light is blinking slowly, that means you're in what we call regulation. Regulation is the point at which your battery bank sees that you're above the voltage regulation set point. I'll talk about that again in just a second. And the turbine the circuit card says to the turbine, shut down, stop sending energy to the battery bank. We don't want to overcharge the battery bank. Stop doing that. And so that's what it does. It's not sending energy at that point to the battery bank because it's in regulation. The next thing you're going to see is if that LED light is blinking rapidly, very fast, three or four times a second. That means it's in overspeed protection. Overspeed protection is the point at which the turbine has sensed that it needs to shut itself down because a storm is coming in or the wind speeds are very, very high, and that's typically around 30, 35, 40. It depends on the gusts and a lot of other factors that circuit card is sensing. But it's got high wind speeds, and it's saying to the turbine, shut down. We want to protect ourselves. We don't want to burn up. We don't want to have anything happen to us. So shut down, then reevaluate after a set period of time. That's anywhere from 30 seconds to 5 minutes, depending on the turbine and the algorithm. And then it restarts itself, and it checks the wind. And if the wind is too high or the gusts are too high, it'll shut down. And you'll know that because of the blinking, of the fast blinking on the turbine. If it's already charged your batteries up so much because you've been in high wind speeds for a long period of time, it'll go into regulation. Or it'll start charging your battery, the light will be solid, and then if the battery bank is full, it'll go into blinking or fast blinking for overspeed protection. So that's what it does. So let's talk about that potentiometer again here. So here's the factory regulation set points for the different voltages, but you can adjust that voltage range if you have a specific battery bank that likes to see a certain voltage. I would say 85% of our customers leave the voltage regulation set point right where it's at. They don't mess with it at all. But this is in your manual when you get the turbine, and it is something you need to know and explain to your customers that you can set that if your sealed batteries or your lithium-ion batteries, or if you have a specific need to adjust that voltage regulation set point, which you might need to do if you have a specific sealed battery, if that battery manufacturer recommends a certain voltage regulation set point. And you can adjust it here by these parameters. It is important to remind your customers and yourself that this voltage regulation will not increase the power output of the air turbine. In fact, if you change the voltage and it's too high, you can overcharge your battery bank and damage the battery. So just keep that in mind when you're explaining this or you're doing this yourself. All right? Now, we did talk about all those things, the amp meter, the stop switch, and so on. In the recent couple months, we've developed a unit we call a wind control panel that makes for very easy wiring for folks who are doing this themselves or dealers in the field that want for easy wiring. You can see it's all combined into one neat little package. We have an enclosure for this. It comes in 12 or 24 volt with a different breaker on there, different amp size breaker for the different voltages. And you can see from the back of it, the wind goes in, battery goes in, super simple wiring. You run your ground down to your battery bank or to an earth ground or however you want to do it. It just makes the wiring very, very simple for the three different components if you want to have an amp meter, a stop switch, and a breaker all combined together. This retails at $199. So just something to keep in mind. So few specs of the turbine. The rotor diameter, like I said, is 1.2 meters. The swept area is about 1 meter. It's a micro turbine, so it only weighs 13 pounds, about 6 kilograms. The startup speed for the turbine is at sea level, 7 miles per hour for the 40 and the Breeze, 8 miles per hour for the 30 and the X. That's because it's a different blade set. The Air 40 and the Air Breeze have a different, little bit wider blade set, so it starts up at lower wind speeds. It does come in these voltages, and it has a 5-year warranty on the turbine, and so on. So this is just some information about the turbine. A little bit about tower height. This is kind of your Wind 101 right here. When you're talking about tower height with any turbine, as you go up in tower height, you're going to get what we call better laminar flow of wind. That's unbroken laminar lines, nice even flow lines of the wind itself. When those lines get broken up, we call that turbulence. And turbulence affects wind turbines dramatically. The more turbulence, the less energy production you get out of the turbine, the less consistent RPMs you're going to get out of that turbine. So obviously the higher you go up, you get better laminar flow, because the lower you are to the ground, the more turbulence there will be off that, what we call surface roughness. That's the trees, the houses, the rocks, the boulders, anything that's on the ground that's going to cause that wind to get turbulent, to get broken up. So, you know, you go up and you get better efficiency out of that turbine. But with a micro turbine, keep in mind that the higher you go up, the higher cost you have in towers, wires, foundation. All those things increase. And when you're talking a turbine that retails for $849, it may not make sense to go up to 50, 60, 100 feet to get, you know, 20 or 30% more power production out of that turbine. It may, in fact, the reality of it is 90% of our turbines we sell are sized at between 27 and 45 feet in tower height. Just because that's the sweet spot for our turbine in terms of tower height. It's not expensive. The wire size, you generally can keep it to number 8 or number 6 wire, and so it just costs less for that turbine to be supported on a tower. So keep that in mind. But you do increase energy production when you go up in tower height. And if you're going to be buying a bigger turbine, a 3K or a 5K or a 10 kW turbine, it does make sense to go up to those high tower heights to get better laminar flow. But with a 200 to 400 watt turbine, probably doesn't make sense. A little bit about sighting. This is, again, a little bit of Wind 101 here. Here's flagging for a turbine. You can tell when you get to a site to see what those trees are doing, or the brush or whatever is doing at the site, and you can tell what's happening. This is called your Griggs-Putnam Index. You can learn a little bit more about that, but that gives you an idea of what the wind speeds are at that site. There's also other indexes that you can use. But when you're siting a turbine, the most important thing to remember is to make sure you put that turbine on the prevailing wind side of the structure and or the trees or whatever. That's the most important thing. So you can see this is the best placement for this turbine on the prevailing wind side of the turbine. If you're behind the building or the trees, you're going to get turbulent effect, so you have to make sure you're above and behind them enough. There's a typical rule in small wind. It doesn't necessarily apply to micro wind, but we call it the 20-50 rule. That's 20 feet above, 250 feet away from any object that's going to cause turbulence, and that's going to kind of get you out of that turbulent effect of that trees or the building or whatever. That doesn't necessarily apply always in micro wind, because we do sell a roof mount kit for our turbine, just because it makes for a very, very easy installation and not costly installation. And some folks are very happy with that. They're happy with the fact that they're going to get a little less energy production out of that turbine being on an outbuilding or a shed or their power shack, but it makes for a very easy installation and very simple and uncostly. So when you're on the water, you can see you have good laminar. See how these are nice even flow lines for that wind. When you're on the water, you have very good laminar flow. So if you're coming off the lake or an ocean or something like that, you're going to see really good energy production out of the turbine because you have very little to no turbulence. There's no surface roughness on the water here. When you're on a hill like this, as that wind flows up the hill, especially if there's no trees or surface roughness on this hill, that wind flows up, good laminar flow of wind, and the wind begins to compress as you move up the hill, which increases velocity, and therefore you're going to have excellent energy production on the hill. But if your house is down here and it's 300 or 400 feet to the top of the hill, it may not make sense to add that extra wire size and so on to get that increased energy production. So you have to look at that. But remember, in the power relationship of a wind turbine, any wind turbine, velocity is cubed in that relationship. So anytime you go from 10 to 11 miles an hour of wind speed, it's not a directly proportional relationship. It's a cubic. So you're going to get exponential increase in that energy production when you go up in wind speed. Now, this is why we don't typically recommend putting a turbine on a building or necessarily directly right on the edge of a cliff, because if you put the turbine right here on the edge of the cliff, you're going to get, as that wind hits the cliff, it's going to push that wind up, and you're going to get turbulent wind across the blade set, and you're going to get a pretty significant reduction in your energy production off of that building, depending on how the building is shaped and the size of the building of that turbine. So that's why you'd want to put the turbine back behind the cliff like this, where that laminar flow of wind begins to come back down. So I often get the question, well, let's put the wind turbine up on our 8-story building because it's going to be great wind up there, but that's not necessarily going to be the case. About 90% of the time, you're going to get big turbulent effect of that wind from that building, and it's really going to reduce the energy production of that turbine. So keep that in mind when you're talking to customers. The secondary thing is, if you're putting a wind turbine on a house, you're going to get vibration associated into that turbine into the house, and if it's an inhabited space, that could potentially, depending on the size of the house and so on, affect the people who are in that house, as well as potentially the structure. So we typically don't recommend putting turbines on buildings unless they're structures that are, that are power shacks or a shed or something like that that's uninhabited. Keep those things in mind. So let's talk about the hybrid concept here. The hybrid concept is something that's really popular in the last year or so in our industry, solar and wind, the renewables industry, because you're combining two power components for off-grid. And this is for off-grid. We typically don't see in grid tie environments wind and solar combined together, except for maybe a grid zero application. But for off-grid, it makes a lot of sense to have those two energy sources coming in, because solar is great, but there are a few aspects. I have solar on my house, and I love it, but there are a few things about solar that are downfalls, which is solar has low output during the winter months because shorter days. Solar has diminished output during bad weather. When you have a storm coming in, you have clouds, and your output in watts is limited. And solar has no output at night, so you have potential with a wind turbine to produce energy 24/7. So wind power is great, especially when solar is reduced, because the average wind speed is highest in most places in North America anyway. Obviously that changes depending on where you are, but if you're in the United States and Canada, this typically holds true, that you have the highest wind speeds during the winter months when your solar is reduced. Your air density is higher during winter months, which increases the energy output of the turbine, because the higher the air density, the more energy you have, the more power you have in the wind, so therefore you're going to have a higher output. That's evidenced by this equation right here. This is the wind power equation for our wind turbine and anybody else's. So it's the combination of air density, velocity, wind speed, which is here, you can see it's cubed, right? So this is probably the most important factor, and the swept area of the blade set. So the bigger the swept area, the more wing you have in the wind, as we say, the more energy you're going to get out of that turbine. So when you're looking at wind turbines in terms of the energy production, the bigger the swept area, the more energy production. So our turbine has about a 1 meter swept area. So, that's part of the calculation. Wind on average is stronger during inclement weather. So when you have bad weather, you're going to typically see higher wind speeds, and wind does frequently blow in those long winter nights, especially in places like North Dakota, Montana, Wyoming, etc. You have those long winter nights, and you have that wind blowing, and you have energy production to your battery bank if you're off-grid. So we're going to look at these 4 factors, these tenets right here of this this argument that you should combine wind and solar together. So the first thing is wind is complementary. So you have, this is your classic complementary power curve, right? In the summer, lots of solar, not a lot of wind, but in the winter, it's opposite. Lots of wind, not a lot of solar. That's the essence of the hybrid argument, the complementary curve of wind and solar. Here's a wind resource map for winter. So when we're talking about a hybrid system and adding wind to it, we only look at the winter months, because it doesn't matter what that wind turbine is going to be doing in the summer, because you're going to be getting your power production, unless there's a storm, and generally you're going to have wind in that storm. The power production is going to be primarily 90% of it from solar during the summer months. So winter is when you need the extra help. So we're talking January, February, November, December are the times we look at for wind speeds. Okay, so you can see in the winter months, the majority of the United States here, because they're dark blue in the middle of the United States, has pretty good winter wind speeds. The darker the blue, the better the wind speeds. So along the coastline, here up in the northern latitudes around the Great Lakes, the middle of the country, that's why you have a lot of the big wind turbines here in the middle of the country, because you have good wind speeds here in this part of the world. So first question you're going to ask your customers when you're talking about you're talking about adding a wind turbine into the mix of their off-grid system is, well, what's your wind speed? That's the first question, because if they don't have a good wind speed, which about 60% of the customers will not have a good wind speed. And when I'm talking about good wind speed, I'm talking about 10 to 10.5 miles per hour average winter wind speeds. That's kind of the cutoff that we recommend, 10 to 10.5 miles per hour. In meters per second, that's 4 to 4.5 miles per hour. Meters per second of average winter, again, winter, not average wind speed, but winter wind speeds. So how do you figure out this information? Well, we have created a source, what we call the U.S. Wind Calculator. We also have it for Canada. And we're looking at 239 NREL locations in the U.S. for our U.S. calculator. And then we create an algorithm that gives us the wind speed extrapolated down to 10 meters, which is about the height you're going to be installing that wind turbine at. And it's going to help you to determine if your customer has a good wind resource or not. You can get this by going to our website. The URL was on that slide, but it's primuswindpower.com. And then you click on support, and you go down to the U.S. Wind Calculator, which is right down here, as you can see, U.S. Wind Calculator. And so this is what comes up. And when you get to the U.S. Wind Calculator, you click on this drop-down menu, and you pick a particular site to see what's going on at that site. So there's 239 of these sites, so you ask your customer, okay, where are you closest to? It's all in alphabetical order by state. And here, if I have a customer that's close to Nome, Alaska, I'm going to say, well, let's look at Nome, Alaska. Oh, well, you have pretty good winds in Nome, Alaska, I would say. Here you're above 10 in January, February, as well as November, December. So this is I would recommend a wind turbine in the mix in a hybrid situation for this particular customer. Now, if this customer is in, say, Florida, most places in Florida, as you can probably imagine, unless you're on the coastline, are not a good fit. Sorry, I can't remember my alphabet. E, F, G, H. There we go. For Tampa, Florida. Here we go. Let's look at Tampa, Florida. So you can see in Tampa, Florida, they're at no point, even in the spring, are they above 10 miles per hour. So probably not a good fit unless the customer has just got absolutely wants to have wind, but you need to definitely let them know that that's not a good wind resource in Tampa, Florida. And you can look at the kilowatt hours per day that they're going to produce from the wind turbines. You can see not much, as well as the amp hours per day. And it gives you this for the different voltages and the different turbines. Pretty good tool to use. Helps you with sizing the system as well as recommending whether or not they're going to be a good candidate for a hybrid system. 99% of our systems are hybrid systems. In hardly any cases do we recommend that they go with a wind-only system. It makes sense to go with a hybrid system. Let's look at Kailua, Hawaii. This is interesting. Here, I just want to show this to you because most places across the United States and Canada, you have really good winds in the winter and not much wind in the summer. But here, a little different phenomenon. As you can see, they have lots of good winds in the summer, but the wind definitely dies down in the winter. Now, all the way through, they're above 11 miles per hour. So most places in Hawaii are good candidates for wind because Hawaii, because it's an island and have the coastal winds and so on, they're going to be a good candidate for wind. Let's look at one last one, and this is Billings, Montana. Billings, Montana is right here, and this is the classic curve for wind. You can see, whew, that's a lot of energy production in January right there. January, February, and then November, December, they're well above that 10 mile an hour mark. And so Billings, Montana is a classic candidate for a hybrid system. So this is your classic complementary curve, right? Not much wind in the winter, whole lot of wind in the, not much wind in the summer, a whole lot of wind in the winter season. So, so good stuff to learn there from that. I just wanted to show that to you. That's available, again, 239 NREL locations. We also have this for Canada, so you can go to that primuswindpower.com, go under support, and we have a Canadian calculator as well that gives you that same information. There's a YouTube video to kind of show you how to use it, but it's really simple. It's basically using the Canadian Wind Resource Energy Map, which is this tool that they have throughout Canada. And again, there's a YouTube video to show you how to use it. It's really simple. And it gives you winter wind speeds as well for the Canadian resource map. We also have maps for Europe, and because we sell all over the world, New Zealand, Australia, we don't have a tool for those places. That's something that we're looking at developing. The Mexico and Latin America tool will be next, but it's something we're looking at developing. I talked about air density before. This is just a quick slide to show you that as you get colder in temperature, the air density increases, and remember, the colder it is, the more dense the wind is, the more power you have in the wind. Remember that equation, power equation, air density is in there. So you're going to get better production generally in the winter months, especially when it's colder. Winter months also, you have more weather conditions, you have more bad weather. So these are just 3 slides showing you different places on the planet where you have weather conditions, and just looking here at Rapid City, South Dakota. So this is the solar energy during the day. This is wind energy, and you can see as the solar energy decreases, so you have less light, meaning storms, clouds, the wind energy increases. So you can see this curve going up. Different places have, it's, obviously a more improvement. Here in Rapid City, South Dakota, it's a 23% improvement. It's different for different places, but the overall essence of this data, and this is 30 years of data from NREL, that basically says when it's less sunny, it tends to be more windy on average during these bad weather conditions. So something to keep in mind. Here's some actual complementary curves using the NREL data, 30 years of data at all the 239 sites. And here's Fargo, Billings, Montana, Minneapolis, Minnesota, and you can see the red is the wind, the blue is the solar. Classic curve here, right? Classic complementary curve Lots of sun in the summer, not a lot of wind. Lots of wind in the winter, not a lot of sun. That's why hybrid systems are important. The solar day, you all know this, but you know, blue is June, red is December. You have a huge difference between how many light hours you have during the winter than you do during the summer. That's why most people size their systems for December 21st, the shortest day of the year. And so when you're talking about a hybrid system, you can make that battery bank a little smaller. You can make that PV size a little smaller. You can potentially make the controller a little smaller because of the fact that you have a wind turbine in the mix, and you know in most places you're going to get most of your wind in the winter, and most of your sun is not in the winter. So this is just illustrating that point. It makes a lot of sense. If you have a decent wind speed, 10 mile per hour or more, that you add a wind turbine into the mix, because you're going to make up for that cost in a little less battery, a little less PV, maybe a little smaller controller. You're going to make up that cost up, and you're going to have redundancy and backup in your system. So something to really consider. Nighttime power production too. Remember, wind turbine, you got 24/7 potentially of power production, and especially during the winter months, it's often likely you're going to have power production. As you can see here, Cheyenne, Wyoming, during the winter months of 1990, it's pretty much blowing 13 miles per hour or above throughout the winter months on average in Cheyenne, Wyoming. I mean, it's a no-brainer if you're in Billings, Montana, Cheyenne, Wyoming, North Dakota, a lot of places, especially in the northern latitudes, Canada, to have a wind turbine, Hawaii, to have a wind turbine in the mix with your solar system. Here's kind of the crux of the argument. We all know that battery banks are probably the most expensive part of the system. And if you can keep that battery bank from discharging below 30, 40, 50% depth of discharge, you're doing that battery bank a huge service, because you can see from this chart the number of cycles really starts to drop down as you drop below about 30 or 40% of depth of discharge. If you can keep that battery bank up high in terms of battery voltage and depth of discharge, you can really elongate the life of that battery bank. And as we know, those sealed battery banks now only last about 5 years, and even less if you're deeply discharging them. And sealed batteries are expensive. So if you're going with a sealed battery bank, or even a FLA, a flooded lead acid battery bank, it's so critical to try to keep that depth of discharge between 30 and 40% or less. And you're going to be able to do that because your depth of discharge is going to be the lowest during the winter months and the storm periods, when you have a load and you have very little energy production into that battery bank. So that's really important part of this argument for adding a wind turbine in the mix. Nice thing about the air turbine, it has all integrated controls, so you don't have to have a separate charge controller. You can wire it directly in the battery bank, and it'll easily retrofit into most existing systems that you have. The air turbine's been around a long time, so lots of longevity, benefit for lots of improvement and tweaks to the turbines. So the turbines we're producing today are quite robust and reliable. Here's the application guideline. I'm kind of moving quickly here because we're a little short on time, but you know, when you're talking about a marine turbine, here's the turbines of choice. When you're talking about a land, anytime you have sound requirements, if it's going to be in a application where people are going to be around the turbine, you want to go with an Air Breeze or an Air 40. They are by far the quietest turbine. Industrial applications, you want to use an Air 30 or an Air X. And in very, very high wind regimes, this is about 2% of the time, you could talk about adding a TriStar controller and a dump load into the turbine as part of the wiring. Not necessary in most applications. If you have questions about this, email me or call me and I can talk to you more about how this works, but it's only about 2% of our applications. Feature comparison chart here. As you can see, quiet operation for the 40 and the Breeze. You do have some sound associated with the 30 and the Marine. Blade sets, The 40 and the Breeze here, it's a wider blade set, so it operates at lower wind speeds, more energy production at lower wind speeds, 30% more surface area, and quieter. The 30 blade set is designed to operate at higher wind speeds, industrial applications. It is louder, but it is much more of a robust industrial turbine, so something to keep in mind. Here's your power curve for the turbines. Remember, anytime you're talking with a wind turbine manufacturer, you want to look at the power curve, and you can see this big spike here is with the 30 and the AirX turbine is because the Air 30 and the AirX turbine operate at a higher RPMs, 400 RPMs max versus, 1800 RPMs max versus about 1000 RPMs for the Air 40 and the Breeze. But you're going to have better energy production at lower wind speeds for these turbines. This is the energy curve for the turbine. You can see again the orange is the 40 and the Breeze, the blue is the 30 and the AirX Marine. Different blade sets here, different operating parameters, RPM, so that's why at these lower wind speeds again, the 40 and the Air Breeze are going to offer you more energy production. This is the sound. This is the sound for the turbine. So the blue is the turbine operating, and the green is the background noise. You can see it's all, the blue and the green kind of all blend together until you get to about 25 miles per hour, and then you start to hear that turbine a little bit, but it doesn't go above about 65 decibels. So a good indicator for that this turbine is quite quiet. So let's look at some pictures in the last couple minutes here. This is how it all started with small off-grid cabins. This is a 45-foot guide tower kit, 8 guy wires down to the bottom of the turbine, running directly in the battery bank, powering up some lights and the pump maybe in this off-grid cabin. Here's an off-grid application. This is a 27-foot tower kit, 4 guy wires, you can see. This is an old Air 30 turbine from the mid to late 90s. Very easily portable for this yurt in this particular off-grid family. Do a lot of sailboat applications. This is a mast and stay kit on the stern of a sailboat. About 30% of our market is sailboats. Here's some more ways that they mount the turbine on a sailboat. This is off the radar arch. This is off a trimaran, off the middle portion of the trimaran. This is off the mizzen mast, just mounted right off the mast itself. These are 2 turbines and 2 solar panels on a cruiser going off to across the Intercoastal Waterway, jumping over to the Caribbean or the Bahamas, and so on. Typical application for a cruising sailboat is they'll often have a turbine or 2 combined with solar. Here's 2 turbines on a sailboat. You can see on the back of the sailboat here on the radar arch, they have the solar, and then 2 turbines on the mast itself. This is San Carlos, Mexico, in the Sea of Cortez. This is a parking lot application with parking lighting, wind and solar combined together. This is in Colorado. Oil and gas, like I said, is burgeoning industry for solar and wind. This is a small Schedule 40 pipe. It's about 20 feet in elevation. Not much surface roughness here, so they don't have to go very high. Plus the winter wind speeds are screaming here, so they don't have to go very high. Same thing over here. Solar and wind combined together in this oil and gas operation. These are power skids, again, for oil and gas and telecom. Battery box at the bottom, controller, 500 watts of solar, a guide tower here, a lattice tower here going up to a stub pole monopole with a air turbine on the top. This whole configuration tilts down for easy transport, but you can see these just get picked up and dropped off for remote power at telecom and oil and gas sites. This is a mining operation where they have solar and wind combined together in a tailings pond. This is Antarctica, where they have multiple turbines on this Antarctic Science Station. You can see the vertical face of the wind turbines here. We're at the bottom of the world, right? South Pole, Antarctic. So multiple turbine configurations, you want to make sure you put them at different elevations so that because the wind direction is coming from here, it's an upwind turbine, right? So this downwind turbine doesn't get shaded, downwind shadowing effect from the upwind turbine. So it's important to have them at different elevations so you have no downwind shadowing effect. Again, here for this buoy application, you have solar and wind, 2 different elevations, so you have no downwind shadowing effect from the upwind turbine. You are going to have some turbulence off this equipment right here, as you can see, if the wind is coming from this way. But this buoy is swinging around, so the wind's going to be coming from all kinds of different directions, right? So something to keep in mind. This is a telecom application with solar and wind combined together. This is a railroad application for off-grid switching platforms and so on. For years, they just had a propane generator. Now they've been installing solar and wind for these off-grid switching and different configurations they need for the railroad applications. You can see it's a cloudy day here, stormy, cloudy day, so that solar panels aren't doing so good, but wind turbine tends to be spinning. And here is a RV application. I just like this picture, Sea of Cortez, Mexico. This guy's got solar and wind combined together. And then here is Alaska. You can see very short tower. That's probably a 15-foot, 16-foot tower, but that wind turbine is spinning like crazy, and that solar panel, not doing so good. Directly wired into, you can see the battery bank right there. So very simple application, very critical, especially for winter conditions. So there you have it. Sorry I was a little bit later than expected, but pretty close to on time here. And now what I'm going to do is I'm going to unmute you all and answer any questions that you might have. And I just want to also say I appreciate your time today and listening to the webinar.